So this is on section 5.3, which is on small sample confidence intervals for a population mean. So before we start talking about confidence intervals, let's first talk about students' t-distribution. So the point of students' t-distribution is to approximate normal distribution when the sample size is small. So small means less than 30, according to the central limit theorem. So how it works is the t-distribution takes two parameters, nu and alpha. So nu, the Greek letter nu, is the degree of freedom. And as nu gets bigger and bigger, the value of t nu comma alpha approaches the value of z alpha. So technically, for each value of nu, there should be a table, but there'll be way too many tables. So instead, at the end of a book, you can find a t table for each value of nu, and for some certain values of alpha, we can find a value of t. So for example, if we want to find a value of t, let's say 4 and 0.025, this value we'll need later. Then you look for 4 and 0.025, so 2.776 is the value we need. Let's say instead we're looking for the value of t 15.01, then we look for the row 15 and the column 0.01, so 2.602 is the value we need. Alright, so now we know how to use the t-table. We can start talking about confidence intervals. So let's suppose we have a small sample. Small, again, small means no more than 30. And this is a very important assumption. So if the sample is small, then we have to assume the sample comes from a normal distribution. Again, if we don't know if the sample comes from a normal distribution, then we cannot construct the confidence interval. So this is a very important assumption. But with that assumption, then we can construct a level 100 times 1 minus alpha % confidence interval. So we have our usual x bar plus minus, we have our usual standard deviation divided by the square root of the sample size. But here, instead of z, we have t with degree of freedom n minus 1 and alpha over 2. So degree of freedom is n minus 1. Right, so that's our formula for confidence interval. But in a rare case, so sometimes, for some reason, you know the true value of the standard deviation, sigma. If we know the true value of sigma, then we use sigma instead of sample standard deviation. And then we use the value of z instead of the value of t. So the confidence interval looks like what you have learned before. It's x bar plus minus z sub alpha over 2 times the standard deviation divided by the square root of sample size. So this is our old formula. If we know the true value of the standard deviation, sigma. All right, so let's do an example. So remember, we have to assume the sample comes from a normal distribution. So let's assume, let's say, human IQs are normally distributed. Again, without this assumption, we cannot construct the confidence interval for small samples. So now we have this assumption, and let's sample a small number of people. Let's say sample 5 people. And then let's say their IQs are 115, 112, 106, 101, and 95. And you can use the calculator to calculate the sample mean, which is going to be 105.8, and the sample standard deviation is equal to 8.1. So now we can construct a 95% confidence interval for the population mean, which is the average human IQ. So we have our x bar plus minus t, n is 5, so degree of freedom is 4. We're talking about 95%, so alpha over 2 is 0.025. And we have our usual standard deviation divided by the square root of sample size. And if you remember from previous page, this value is equal to 2.776 according to the table. And all the other values we know. This is 105.8, this is 8.1, sample size is 5. So we have all the values. We can use the calculator to calculate the confidence interval, which is going to be 105.8 plus minus 10.0559. So let's recall that the purpose of confidence interval is to catch the true value of population mean. So in fact, our confidence interval 105.8 plus minus 10.0559, it does catch the true value of population mean, which turns out to be 100. So it's a good thing that our confidence interval works. All right, so that's it for 5.3. Thank you.